Okay, we're going to be working on number 14 from the AP formatted practice test. And just a heads up, as I go through this one, that there is a mistake on the answer key. They're off by a factor of 10, and we'll cover that as we get through it. Excuse me. I'm at home, so you guys get to listen to me open a Diet Sunkissed Orange. So, all right, that'll help with the allergies. Clear the throat. Okay, so a 3 kilogram block is fastened to a vertical spring that has a spring constant 800 newtons per meter. 1.2 block rests on top of it. Okay, the key here, and this will not pop up immediately, but it will pop up later, is that the word fastened. This thing is fastened to here. So wherever the spring goes, the mass goes. That is not true for the top block. So you can imagine if the spring were to spring too hard, that maybe the top block would fly off, but that can't happen to the 3 kilogram block. So just that's not going to be important for right now, but it will be important later. So, A, when the blocks are at rest, how much of the spring is compressed from its uncompressed length? So this is going to be Hooke's law. As the force of gravity, well, I guess I can just do this way. There's the force of gravity down, and then there is going to be the spring force up. When the blocks are at rest, those two forces are equal. So Fg will equal F of the spring. And this means that Mg is going to be equal to Kx. And again, I'm taking off the negative sign on Hooke's law because I know what direction the force points. It's opposite the displacement. So I'm just going to solve it in terms of magnitude. Doesn't matter. So we're trying to figure out x. X is a compression length. So mg all over k has got to equal delta x. The mass here is 4.2, or so 3 plus the 1.2 times 9.8 divided by 800. And if you do this, as I do this, you get 0.051 meters. The answer key said that 0.51. That is a simple mistake on their part. So it should be 0.051. Unless there's something that I'm seriously missing, but it wouldn't be the first answer key that has a mistake. And you have to realize that, just a heads up, when you do take these answer keys sometimes out of AP websites, or you take answer keys out of other teachers' websites, oftentimes the answer keys are done by graduate students. These are students that are trying to basically earn money as they're going to college, and so they get paid per answer key. And so oftentimes they have an incentive to go quickly to make their answer keys, and obviously they want to do a good job and get them right, otherwise they'll be out of work. But you have to understand there's a bit of a time pressure when answer keys are being generated. Anyways, and plus, honestly, we're all human. So we all make mistakes anyways. So anyways, answer is A. The answer for A is 0.051 meters. Okay, so now the blocks are pushed down so that they oscillate to determine the frequency of the oscillation. So now we can just simply apply that this idea 1 over 2 pi square root of, this would be k over m. And so now when you calculate that out, so I'm going to go 800 divided by 4.2, take the square root of that, divide it by 2, divide that by pi, and I get about 2.2 hertz. So that would be the answer for that one. Just a little word to the wise that if you're trying to remember the frequency formula, is it k over m or m over k? Same thing with the period formula, is it k over m or m over k? Ask yourself simply, if I have a really stiff spring, is it going to go boing, 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 or is it going to go boing, boing? So you see that the higher the value for k, you should have a higher frequency. That means k goes on the top. It's the same thing for period. If you have a really heavy mass, shouldn't the period be longer? So you know that the mass should be on the top. Anyways, just a little quick thing that you to help you remember if you're ever not sure if it's k over m or m over k. Determine the magnitude of the acceleration. Okay, so this is the fun one. This is the interesting one. So the question here is, I'm actually going to draw it off to the side. is that if you think of this as equilibrium, and let's draw the spring right here, and this will be the max displacement here. We'll call this the max displacement up here, and then this will be the whatever, the ground. So if the top object, or if the top box is just sitting on the top of it, when it's down here like this, we're not in ever any danger of the top box losing contact, because the top box is accelerating downward, the spring is accelerating upward, and so there's a natural sort of push-pull where the object is definitely going to be in contact, in fact, have a greater normal force on it than it would anywhere else. The only time it could ever really lose contact is at the very, very top of its oscillation. So let's see what's happening here. So let's imagine we're here. Now, it doesn't matter what the acceleration of the spring is for this first box, because the first box is attached to it. It is fastened to the spring. So it doesn't matter at all what the spring force will provide to the 3 kilogram box, because it's not going to lose contact with the spring. However, the top box is free to move. And if you think of the motion right here, at the moment it gets to the top, it has its maximum acceleration downward, and its initial velocity is 0. Right at the very, very top, both objects have a velocity of 0 at the very, very top, at least provided by the spring. What that means is that this top box is in free fall. So this top box is in free fall with acceleration of 9.8 meters per second squared at the very, very top. As long as this bottom box, is not accelerating greater than 9.8 meters per second, then you're gonna be in contact. So we want the acceleration to basically be less than or equal to 9.8 meters per second squared, because again, at the very, very top here, this top box is in free fall, and it has to at least, the bottom box has to be at least in free fall or less than that for the contact to be maintained. So 9.8 meters per second squared. How far can the spring be compressed beyond the compression found in part A? Okay, so here's what we're going to do. A couple things. Well, there's several ways you could solve this one. I'm going to refer to my notes for a second to find out which way I did this one. How far can the spring be compressed? Okay. So the way we want to think about this is that we want to set the acceleration at the top of the spring here to be 9.8 meters per second downward. So F equals ma. We want the force of the spring downward to be equal to 4.2 times 9.8. So I believe that's 41 and change, if I remember doing this last night, but 41.16. Okay. Okay. So we want the maximum spring force at the top to be 41.16 newtons. So remember, the spring force is equal to kx. So this displacement right here, delta x, we want that displacement from equilibrium to give a spring force of 41.16, and we already know the k value. So 41.16 has got to equal 800 times x, and I think you will, maybe you won't be surprised by this answer. 41.16 divided by 800. Guess what you're going to get? 0.051 again. Couple reasons for that. One of the main reason you can think about it is, let's imagine this spring in its natural sort of position before you put any mass on it. Okay, let's just imagine for a moment. I'm just going to use the two boxes as one mass. Okay. Let's imagine that you set the boxes on the spring with 0 velocity, right? So they have just the potential energy. That is going to cause the spring to contract. We already figured this out. 0.051 meters. Now we already know that we want the max acceleration at the top to be 9.8 meters per second squared. You could actually rewind the clock. Imagine that you made this into a movie of where you simply placed objects on the spring and it compressed down to this level right here. Rewind that for a moment. You'll see the box at its equilibrium rise up, and at the very, very top, this box will have a downward acceleration of 9.8 meters per second squared, at least an instantaneous downward acceleration of 9.8 meters per second squared, because you simply placed it on there. So it should make sense to you that a compression of 0.051 meters gets you that type of acceleration. Okay, now the only catch is here that this right here is the new equilibrium once you put the boxes on it. So it's not going to oscillate at this moment, right? You want to be able to get the box to go up this high for the conditions to be satisfied. So if this is the new equilibrium and you need the box to rise up 0.051 meters, that means you better press it down an additional 0.51 meters if you want to have that correct oscillation, right? So anyways, that's just the sort of conceptual way you can work through this one, and I think it's a nice way to do it. It's important to understand conceptual understanding of physics. There is one question that I unfortunately didn't get copied off. It's E is asking for, and I'll just write it in here. What's the max velocity? Well, the max velocity, if we imagine this to be the whole range of motion right here to be the top, here be the bottom, and here's the floor. The max velocity is going to be right there. That's where the acceleration is 0. So the max velocity is going to be reached right there. So what it means is that the potential energy of the spring is going to be equal to the kinetic energy of motion at that moment. So you're going to have the I guess do this in blue. 1/2 kx squared equaling 1/2 mv squared. You already know that you've compressed it this 0.051 meters, so that takes care of that. So the halves go away. So 800 0.051 squared equals 4.2 v squared. And let me just crank this out real quick to make sure I got the number that I have in front of me. Squared times 800, yada, 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 divide by 4.2, take the square root. Yeah. So the V should be 0.703 meters per second. And that's how we do 14.